Everyone could take your seats. It's 1:30, so we're going to get underway. So good afternoon, everyone. Great to see such a nice turnout. My name is Kimberly Strong, and I'm the chair of the Department of Physics here at the University of Toronto. It's my very great pleasure to welcome you to the 2024 Welsh Lectures in Physics, which I think are the 47th set of lectures in this long-running series. I'd like to start my remarks with the official U of T statement of acknowledgement of traditional land. I wish to acknowledge this land on which the University of Toronto operates. For thousands of years, it's been the traditional land of the Huron-Wendat, the Seneca, and the Mississaugas of the Credit River. Today, this meeting place is still a home to many Indigenous people from across Turtle Island, and we're grateful to have the opportunity to work on this land. So the Welsh Lectures are named in honor of Harry Welsh, who was both a distinguished molecular spectroscopist and chair of the Department of Physics from 1962 to 1968, which was a period of tremendous growth in the Department of Physics. His association with the University of Toronto spanned more than 5 decades, from his enrollment in the undergraduate math and physics program in 1926, at the age of 16, to his retirement in 1978. Along the way, he supervised 65 PhD students, and his tenure as chair was marked by the introduction of research groups in theoretical, atmospheric, and high-energy physics, as well as the completion of our beloved McLennan Physics Building. Over the course, I can't imagine how that building was built. Just seeing how it's an amazing building if you actually explore all the corners. What they managed to do was incredible at the time, even if it is aging now. So over the course of his 5 decades with the department, he saw it grow from 6 faculty and 12 PhD students in 1930 to 60 faculty and 150 graduate students, following the huge expansion of the 1960s and the 1970s, in which the department really began to resemble the one that we have today. In 1975, on the occasion of Professor Welsh's 65th birthday, the Welsh Lectures were established, and they have since become the major public event in the life of the Department of Physics. The Welsh Lectures give us the opportunity to showcase to the broader community some of the most exciting aspects of current research in physics. Each year, we invite 2 physicists to speak who are known both for their extraordinary contributions to the field and for their skill in communicating the excitement of that work to a broad audience. This year, we're very fortunate to have as our speakers Professor Alain from the Institut at the Université Paris-Saclay in France, and Professor Stephen Kivelson, who is coming to us from Stanford University in California. While today's speakers work in very different areas of physics, each of them is at the forefront of their field, as you'll be hearing about today and tomorrow. Professor Aspect is a pioneering experimental physicist known for elucidating aspects of the quantum world with profound philosophical consequences. Of course, he was awarded the Nobel Prize in Physics in 2022 for experiments with entangled photons, establishing the violation of Bell's inequalities, and pioneering quantum information science, to quote from the Nobel citation. Professor Kivelson is one of the leading figures in condensed matter theory and has made many important contributions in quantum condensed matter physics. He's widely recognized for his pioneering work in the field of strongly correlated systems and superconductivity, particularly high temperature superconductivity, as well as other topics as you'll be hearing about. So I'm just delighted that both speakers have agreed to join us to tell us about their work. As usual, the Welsh Lectures are taking place over 2 days this year. So this afternoon, our speakers are delivering a public lecture. And tomorrow, if you'd like to learn more, you can join us for the more specialized lectures that they'll be giving on their current research. There'll also be a public reception following today's public lecture, which will be held in MP 125, the Physics Undergraduate Lounge, just across the street in the McLennan Physics Building. So that will be immediately after the lectures, and all are invited to attend around 4:30 or so. So before we start our first lecture, I'd like to take this opportunity to thank members of the 2024 Welsh Lectures Committee for all the work that they've done to bring us the lectures this year. So these are committee chair, Youngbak Kim, and Professors Miriam Diamond, Sid Goyal, Peter Martin, A.W. Pete, Ephraim Steinberg, and Zan Su. I'd also like to thank the department staff who've helped with the organization, particularly Helen Iyer, who provided much of the logistical support. I don't think she's here, but she's outside, so thank you to Helen. And then also Eva Chung, who helped out with some of the graphics and the poster, Julian Kamanian, who helped out with the web pages and I think the wall monitors, Supreet Wandawa for social media outreach publicity, Armin Moki for various help with various things and additional ideas, and then Jonathan Hucker and Lillian Leung for their assistance with AV. And so now I'd like to invite Professor Joseph Iwison to introduce our first speaker. So over to you.
Alain aspect needs a little more introduction to this audience, but je voudrais seulement dire qu'Alain était heureux de prendre que Canada est un pays bilingue et donc il est ravi de donner sa conférence en français aujourd'hui. Et je suppose qu'il n'y a pas d'objection de votre part, non? I'm only kidding. Alain's actually a communicator who will do everything, even speak English, to communicate his love of physics to you today. In fact, you may be interested to learn that Alain identifies himself first and foremost as a teacher who, by asking questions, wanting to learn more, eventually touched on the very foundations of quantum physics. In this way, I think he's really a model for us all to follow, no matter what discipline we're studying. Let me just add one more thing, which is that Alain has been a mentor to many people, myself included, and so it's a special pleasure and honor to have him with us today. Please join me in welcoming Alain Aspect.
Thank you very much, Joseph, for this kind introduction. I must say that when Joseph asked me to come and participate in this Welsh lecture, I could not refuse because Joseph was really one of my best postdocs ever. And in addition, he's a wonderful person. Probably you appreciate him here. So thank you, Joseph, for invitation. Thank you, the Université and the physics department for inviting me and giving me this opportunity to be here. It's a little embarrassing because I have been heard that it is a public lecture today, and tomorrow it's more specialized. But it seems that, in fact, the general public is not so much general. Who has not followed the physics courses in the audience? One. Good. That's an interesting distribution. Okay, so you have to excuse me that there will be a strong overlap between what I do today and what I do tomorrow. But okay, maybe, you know, when you are a teacher or a student on both sides, you know that listening 2 times to the same thing is the best way to understand it. Well, it's not to say that tomorrow will be exactly the same thing. It will be a little more technical. But anyway, the spirit will be almost the same. Okay, let us start. And in general, when I have a general public, I start by emphasizing that quantum physics is strange, but not irrational. Why? Because you see in the newspaper quite often, when something is totally crazy, then people tend to explain it by quantum physics. For instance, you know, bending spoon at a distance by thinking hard on it is strange. And so it's so strange that people think that it is a quantum phenomenon, okay? And be careful with that. You will see in newspaper, it's often happen. So what is quantum physics? Well, in my opinion, it's a mathematical formalism allowing one to perfectly describe observed facts impossible to describe in classical physics. Stability of matter, chemical bonds. Stability of matter. Probably most of you have realized, but in case some of you have not yet done it, at the end of the 19th century, physics was quite developed. people knew that matter is made of positive and negative charges. And they knew that positive and negative charges attract each other. So the equation, natural equation is, why doesn't matter collapse on each other? And if you don't have quantum physics, you cannot answer that question. Quantum physics is necessary to understand why the electron doesn't fall on the nucleus, etc., etc. So quantum physics first allowed to describe in a rational way things that people did not understand: stability of matter, chemical bonds, matter-light interaction, and some more exotic property like superconductivity, superfluidity. But what makes quantum physics a real good physical theory is the fact that not only it allows one to render an account of what is already known, but you have in the equations much more than what you put into it. The best example of that being a very good theory is Maxwell equation. Maxwell equation in 1865 was collecting all the known facts on electricity and magnetism. And then in these equations, there was something new. A solution was waves propagating at 300,000 kilometers per second. Nobody had heard of that. It was a solution of Maxwell equation. And then immediately Maxwell, at that time, they knew that the velocity of light was 300,000 kilometers per second. And so Maxwell immediately concluded, we cannot avoid to think that maybe light is an electromagnetic wave. And then Hertz, reading the paper by Maxwell, developed this generator, and that's all. So I emphasize the fact that a good theory in physics is a theory which not only describes what you already know, but it allows you to predict things that you find in the lab. And a best example is entanglement. The experiments that I did were predicted by the equations, and the equation had not be written to render an account of something already observed. And so this is a sign of a very good theory. Moreover, this mathematical formalism allowed bright people to invent devices such as transistors, lasers, integrated circuits, which have changed our society. Young people don't believe that the inventors of transistors, lasers, integrated circuits are brats in a garage in California or elsewhere. They were the best physicists of that time trying to render an account of properties of materials like semiconductors, etc. They got Nobel Prizes for understanding that. And in passing, they also invented transistor, integrated circuits, etc. What is the problem with quantum physics? The problem is that we have no simple image to represent the formalism in our usual space. And this is a difficulty. But once again, do not draw nonsense consequences. Okay, so I am going today to talk of the first quantum revolution and then of the second quantum revolution, while tomorrow will be more focused on the second quantum revolution. So this is the real general public side of the talk, that's the first part. In fact, why do I speak of two quantum revolutions? Because in fact, there are two totally different concepts, which are the root of each of these two quantum revolutions. Wave-particle duality, I will speak a little more about it, which was discovered by Einstein and by Louis de Broglie, is at the root of the first quantum revolution. While entanglement, discovered by Einstein, Podolsky, and Rosen, and Schrödinger almost at the same moment, added his grain of salt, is at the root of the second quantum revolution. And John Bell, of course, played a major role in realizing that it is definitely different from the first one. So let me start with the first quantum revolution. Again, what I'm going to say now is for general public. So if you find it obvious, you should have refrained from coming to a general public lecture, okay? Quantization. Why do we say quantization? Why use that word? That word is associated to the fact that some quantities, which usually we consider as able to take any value, in fact, in the quantum world, this quantity can take only some specific value, some discrete values. In contrast to the classical formalism, which allows us to consider a continuum of such values. For instance, the energy of an ensemble of electric charges, classically it can take any value, but quantum mechanically, no. And plenty of things like that. And the first example of that was light, which is classically described as a wave doing interference and diffraction, but Planck, but more than Planck, Einstein, I can tell you a few words why Einstein more than Planck. Planck made the hypothesis in despair. Some people say, I don't know if it is true or not, if somebody has some hint on that, I would be happy to learn. It seemed that the reason why he called this constant H is because of the German word Hilfe. It was, you know, help, okay? He was despaired, and his hypothesis, he never took it really at face value. It was for him, it's clear by all the texts, it was like a trick to be able to establish an equation. The guy who really said, let us assume that light is really made of grain of energy, least quantum, is Einstein. And so what this says is that light, that we classically describe as a wave, must also be considered a beam of particles with a well-defined energy, which were called photons later by a chemist, by Lewis. It's not a physicist who coined the name photon. Okay. And of course, there was a problem. Einstein, you know, was not stupid. He knew, you know that. He knew of the work of Thomas Young and Augustin Fresnel, showing that light must be considered a wave, otherwise you don't understand interference and diffraction. And so, on the other hand, he had good reason to think that light is made of a stream of particles. What to do with it? Well, to admit the idea of wave-particle duality. And in a fantastic conference in 1909, it was his first appearance on the German Physical Society. He gave a talk, and in this talk, for the first time, he was referring to wave-particle duality. This paper can be found on internet. I encourage you to read this paper, because it's not just saying wave-particle duality. It treats several examples, a la Einstein, and say, you know, when I look at that from a certain point of view, it behaves like a wave, but from another point of view, it behaves like a particle, so it has to be both. Okay. Then, 14 years later, in 1923, well, a little too far. I'm going to speak of de Broglie. Next, transparencies. So here I was speaking of light, now I am speaking of matter. Some quantities can take only some particular discrete values. And the best example is electron orbiting around nucleus. This model of the atom with a nucleus and electron was invented by Rutherford. But Bohr, in 1913, understood that in order to render an account of what is known, you need to accept that only certain orbits are allowed. Why do I say orbit? Because you know that the attraction of the electron by the nucleus is 1 over R2, 1 over R2, just like gravitation. And so it's really like a satellite around the Earth, or like the planets around the sun, etc. But with a difference. The satellite around the Earth can have any altitude, while what Bohr said, and he said to render an account of the spectrum of emitted by atom, etc., that only certain trajectories are allowed. And to understand that, we needed Louis de Broglie, which told us that, in fact, electrons, we think that electrons are particles, but they are also waves, and the condition for which this description be consistent is to demand that there is an integer number of wavelengths on this orbit. This is what selects the orbits, the Bohr orbits. So it is again a condition of quantization. So de Broglie in 1923 made the assumption that for any particle of momentum p, you have a wave of wavelength lambda, such that lambda p equal h. But the man who discovered, when you have a wave, you need to have a wave equation. And the man who discovered the equation is Schrödinger, you all know that. I like really these two photos for the following reason. Look, physics is fun. They are happy to do physics, right? Look, I mean, when you see that, you are tempted to do physics. Wave-particle duality is really something bizarre and strange. In the famous book, Lectures on Physics, Feynman says that's a great mystery. Why a great mystery? Because how can an object both be a particle and a wave extended everywhere? Well, we have to swallow that. And in my opinion, the best way to swallow it is to directly show it by an experiment in the lab. And such an experiment was done by my first PhD student, Philippe Grangier, in '85. In recycling our source of entangled photon, we could produce, for the first time, I insist, single photon wave packets. And with these single photon wave packets, we made a direct demonstration of wave-particle duality. And I show you rapidly what it was. So we have a source here, and we claim that the source sends single photon. And to prove it, we send it on a beam splitter here, and we have here a coincidence circuit able to tell us if we detect on both sides or not, okay? And when we did that experiment with the allegedly single photon wave packet, we indeed observed that the photon can be detected on one side or on the other side, but never on both sides simultaneously. So we conclude that the probability of joint detection is 0. Then we did a slightly different experiment. We have the same source, the same beam splitter, but now we no longer put detector here. We put a second beam splitter and we recombine the path. And in that second experiment, as you expect, we observed that a wave is split in two, recombined, and gives interference. We observe interference by just slightly moving this mirror, changing the path difference between the two sides, and then we observe a modulation of the probability of detection here and there. And I insist, it was the same source, the same beam splitter. So you have that object, which in the first experiment goes either on one side or on the other side. And in the second experiment, you have to accept that it goes on both sides simultaneously. If you think that wave particle is trivial, come at the end and tell me why this is trivial, okay? In fact, what can you do with that? What you can do is listen to Bohr, which tells you, look, my friend, you have to choose. Either you do this experiment or you do that one, and you cannot do both experiments simultaneously. So this is convincing, but convincing to a point, because it is in contradiction with what we are going to see now, with the point of view of Einstein. For Einstein, objects have their own properties. But for Bohr, with complementarity, Bohr tells you that the property of the object depend on the measuring apparatus. And it's a totally different view on the world. It turns out that it works, but we can understand the nature of the debate between Einstein and Bohr already here. Okay. Before finishing with this part, I want to elaborate a little bit about what I mean by a revolution? What was the first quantum revolution? First, it was conceptual. It was based on a new concept, wave-particle duality, and it allowed physicists to make tremendous scientific progress, I already said it, by understanding the structure of matter, by understanding the absorption, emission of light, etc., and exotic property. So it was both conceptual and scientific. And moreover, it was technological because it allowed people to invent transistor, laser, and going to a transformation of the society, going to the society of information and communication. You know, young people, you don't realize, but ask the people who have gray hair here. When we were young, there was no internet, there was no cell phone, nothing like that. Already radio, and I lived the beginning of television. And so really, this invention have totally changed our society, probably as strongly as the invention of the heat engine in the 19th century. So for me, a revolution has to be conceptual, a physical revolution based on physics has to be conceptual, scientific, and technological. And we will see if the second revolution has the three criteria or not. So the second quantum revolution is based on entanglement. I check the time. How am I doing with time, Joseph? Huh? No, but I don't quantitatively, how much? You know, when it was my postdoc, I was like, Joseph, you say it's fine. No, tell me the number. 37 already? What? Ah, okay, very good. Entanglement. Entanglement, so you will see that tomorrow again. Entanglement, to describe it, I will use a scheme which we call Einstein-Podolsky-Rosen Why bomb? Because in the initial Einstein-Podolsky-Rosen presentation of the situation, it was continuous variables, position, and momentum. And it's not convenient to really express what is really entanglement. And David Bohm discovered that you can re-express the Einstein-Podolsky-Rosen so-called paradox with spin 1/2 particles. And spin 1/2 particles, when you measure spin 1/2, you can have two values. And there is something which is equivalent to that, is measuring the polarization of a photon. When you have a photon, well, you know what is maybe not everybody knows what is measuring polarization. If you have a beam of light, the electric field vibrates perpendicular to the propagation of the beam. And you have an apparatus, which is a polarizer, which allows you to know what is the direction of the electric field. More precisely, you have an axis of measurement, and if the polarization of the beam is along that axis, the light will go up. If it is perpendicular, the light will go down. If it is somewhere in between, a fraction will go up and a fraction will go down. But if you have a single photon, you are not going to have a fraction of the photon up and a fraction down. It will be either up or down. Up, you say, I find this result. Down, you say, I find that result. That's quantum mechanics. You measure something, you have two possible values. Okay. So we are going to measure the polarization of the first photon. It has a twin brother, which is emitted in the other direction, the other photon, and we measure the polarization. The polarizer can be oriented along direction A. This one can be oriented along direction B, okay? And we will see what happens. Now, when you have entanglement, this is a discovery of Einstein-Podolsky and Rosen. You can think of a state like that. So when I have a general public, which you are not, I tell them, look, you are even going to understand this wonderful notation that was introduced by Dirac. XX describes a pair of photons going like that. YY described a pair of photons polarized along Y. And the entanglement is the fact that if XX exists and if YY exists, then also XX plus YY can also exist. And at this point, sophisticated people who know a lot of things say, oh, of course, it's, no, it's not two photons like that. Because if it was two photons like that, I could write it as the product of a first term describing a photon like that by a second term describing the second photon like that. And it is not the case. If you know a little bit of mathematics, you will realize that it is impossible to factorize that. So there is no way in such a state to say the first photon is like that and the second one is like that. It's only a slight exaggeration to say that this is as astonishing as the Schrödinger cat, which is both dead and alive. A small difference is that in the Schrödinger cat, there is more than two particles. But apart from that, it's just as surprising. Okay. So Einstein, Podolsky, and Rosen discovered that this kind of state is allowed. And when you have such kind of state, if you study well your course in quantum mechanics, you know that you can calculate the probabilities of finding +1 or -1 here, and similarly on the other side. And if you do your calculation well, you find 1/2 independently of the orientation. That is that whatever you do here, you find either +1 or -1 with the same probability, same on the other side. So it's just like you have two people tossing coin. One people is tossing coin here, another one is tossing coin there, and look at it, looks completely random, But there is something more interesting that you can calculate. It's a joint probability. Joint probability to find +1 here and +1 here. And what you find is that if you find +1 on one side, you are sure to find +1 on the other side. And -1, -1. And so you have what we call a strong correlation. But that strong correlation is just like a tricky coin toss. Look, think of it. You have a guy throwing a coin, and you have a guy throwing a coin here, okay? You look at here, it's random. You look there, it's random, but looking from the back, you have to admit that when he gets heads, there is heads. When he gets tails, there is tails. This is really surprising. You want to find where is the trick. You are pretty sure that there is a trick. You want to find the trick. Finding the trick is doing physics. You want to find an explanation for that. Okay. What is the explanation? Well, I told you, this can be calculated. So the explanation is in the equation. Some people are happy to get equation, solve the equation, and nothing else. But I am not that kind of physicist. I am a physicist who, on the one hand, likes to do calculation and find solution, but on the other hand, I like to have images to support this calculation, to visualize this calculation. And then you bump into a very serious problem. If you take the easy way of doing the calculation, that is to say, starting from the state that I wrote, projecting it on the result you get and taking the square of the modulus, okay, young people who take courses in quantum optics, it is what you learn in the first courses, okay? You get the right result, the result that you expect, but how can you make an image out of that? I don't know, because the calculation is done in a space, which is called the tensor product of the space describing the first particle by the space describing the other one. So you are in this abstract mathematical space. It works very well in that space, but, you know, to make an image in my space, I don't know how to do. Well, in fact, I know, I will show you at the end, but a priori, I don't know. And it is related to the fact that we cannot identify individual property for each photon. But on the other hand, you know, even smart theorists who tell you, you have to calculate, you have to calculate, you have to calculate, make statements. So it was a case of Asher Perez, who is absolutely orthodox, etc. But in his book, he writes a statement which is quantum phenomena do not occur in a Hilbert space. They occur in a laboratory. And I have a laboratory. I have a source here. I have a polarizer at 6 meters. I have a polarizer at 6 meters. I want to have an image in my laboratory, okay? And so I demand an interpretation in real space. And it is at this point that we have the reasoning of Einstein-Podolsky-Rosen. And they tell you the following thing. Look, if you have two particles which have interacted, and now I make a measurement here, and I make a measurement there, and the measurements are correlated, there is an obvious interpretation, which is to say that from the beginning, the two particles have a common property. That property determines the result of the measurement, and that's it. For instance, let us think again to our people throwing coins. If the coins have been given by somebody at the center, and the somebody at the center give one coin to one and one coin to the other one, there would be an obvious explanation. Sometimes he gives coins with two heads, to this one and this one. So they throw it, they find head, of course. And another time it would give two tails and face and coins with two tails on each of the people. That would be an explanation. This explanation is perfectly rational. That's the explanation that doctors or biologists invoked before being able to look at chromosomes. They already thought that if twin brothers have the same color of eyes, or the same color of hair, or the same disease for certain disease, they concluded that it was due to the fact that they have the same chromosome. So you see, this idea is absolutely scientific and rational. So the idea is the following. From the beginning, the two photons share a property called lambda, and this lambda determines the result here and determines the result there. And at this point, it's easy to understand that we can have a correlation. Okay, but this amounts to completing quantum mechanics. Why did Einstein wanted to show that you need to complete quantum mechanics? Because Einstein did not like the idea that quantum mechanics makes probabilistic prediction. It's not to say that Einstein did not like probabilities. One of these most wonderful papers in 1905 is about Brownian motion, and it is a masterpiece of probability. So he liked probability, but he thought that probability is convenient, is a tool for describing situations which are more complicated, and it's a way to simplify them. For instance, let's suppose we want to describe the motion of the molecule of nitrogen in this room. It's absolutely impossible. So we will use a law of probability, saying the probability that the velocity is between 300 and 310 meters per second is, I don't know, 5% or something, etc. But we have no doubt that each molecule has its own trajectory. That was the idea of Einstein. He said, look, quantum physics doing probabilistic prediction, the fact that it gives probabilistic prediction means that it is a kind of statistical physics and that there exists below a more precise structure which is to be determined. And he thought that by this reasoning, he had shown that you need to have a substructure. And at this point, Bohr immediately disagreed. Bohr said, you cannot complete quantum mechanics. If you complete quantum mechanics, it will lose its consistency. But the point, when you read the paper, is very easy, okay? It's a physical review. And physical review, you have prologue, so just go and look at the paper of Einstein-Podolsky and Rosen and look at the paper of Bohr. The reply of Bohr was more philosophical than really scientific reasoning or something like that. Basically, it boiled down to what I told later, which is to say, what you observe is, or the nature of the object that you observe is in part determined by the measuring apparatus. While Einstein, on the other side, thinks that the photon, when they are emitted, they have their own property, period, and their property are not going to be determined by the measuring apparatus. Anyway, to make a long story short, there was a disagreement, and this disagreement could not be settled as clearly as a previous disagreement in 1927 by just a scientific reasoning. It was more about interpretation and epistemology. And as a result, the debate between Einstein and Bohr was never settled. I mean, Bohr could never convince Einstein and vice versa until their death. But moreover, the debate did not draw much attention by most of the physicists. And there are good reasons for that. First, quantum mechanics was accumulating success. So people were using quantum mechanics and it worked. So you are busy, doing your job, you observe something in the lab, you have an interpretation, vice versa, you predict something in the lab and you observe it. So, it works very well, but I think that the major reason why the people did not care is because it sounded to be just a matter of interpretation. Einstein did not object against the calculation of quantum mechanics. He just said, I want to have a picture below it. And because they all agree on the calculation and only disagree on interpretation, people have a better thing to do, going to the lab, make calculation, than thinking about the debate between Einstein and Bohr. Almost 30 years later, in 1964, so the EPR discussion was in 35 and lasted until the end of these people. In 64, John Bell made a fantastic discovery. He made the discovery that a debate which sounded to be just epistemology, in fact, was a scientific debate. Why? Because he could show that any model in the spirit of what I explained, that is to say, it's a joint property between the two photons that will determine the result of measurement here. He could demonstrate that any model of that kind predicts correlation, which can be strong, but there is a maximum limit to this correlation when you consider several angles, okay? And these limits are nowadays known as Bell's inequality. A certain combination of the correlation cannot be bigger than a certain value. And then he discovered that in the Einstein-Podolsky-Rosen situation with photons, or with spin 1/2, it's the same, he discovered that for certain type of quantum prediction, you get correlation bigger than that limit, okay? And so now you have a quantitative, Joseph, a quantitative conflict between following the idea of Einstein or believing in quantum mechanics, okay? And that was, so you can settle the debate by an experiment. So in fact, there were a series of experiments. The first series was done in the 70s by pioneers, Clauser, Pipkin, and Fry. And here I show you John Clauser. He was young in his lab. It was 50 years ago, and the experiment was difficult. I don't want to go into details, but he found a result in agreement with quantum physics and violating Bell's inequality. There was discussion for a while, because Clauser was in Berkeley, Pipkin and Holt were in Harvard, and they had opposite results, which is not surprising, okay, between West Coast and East Coast. It is not a surprise. I disagreed. It turned out that the West Coast was right in these circumstances. Okay. But the experiment was really quite different from the ideal scheme that I have presented to you. And this is why I embarked into a series of experiments that I call the second generation. It was done at Institut. And here you can see Alain Aspect 40 years ago. So it's the same as me, okay? But it was 40 years ago. And so my experiments were definitely closer to the scheme that was discussed by Bell and the other people. And the reason why I could do that is because I could build a source of entangled photon of unprecedented efficiency, purity, etc., etc. Just to give you an idea, it took me 2 minutes to get an accuracy of 1% of my correlation measurement, while for Clauser, it took hours, okay? And when you can do an experiment in 2 minutes rather than in several hours, life is beautiful. It was beautiful. So I could, for the first time, do an experiment with that scheme, which is a scheme that I have presented. That is to say, a scheme where you indeed measure the +1 and the minus output. In previous experiment, you could only measure the +1 output. So you need to remove the polarizer, compare with and without, calibrate, etc. It's complete. Here, it's directly. You do a measurement, you have the correlation coefficient. The last experiment that I did, which is the one which was really considered by the Nobel Committee, is an experiment in which I could change at the very last moment the orientation of the polarizer. This was a suggestion of Bell to do that, because the idea is that you don't want any possibility of an interaction, of an unknown interaction between the two ends. And one way to cut that possibility is to change the orientation at the very last moment, so that the information of the value of the orientation that you select here has no time to influence the result on the other side. And similarly, it cannot influence the way in which the photons are emitted. And rather than turning a polarizer, which was impossible at that time, I found a trick, which is to build a switch, allow either to send light here towards the polarizer in orientation A, or to send light towards another polarizer in other direction, A prime. And if the switch is fast enough, and it was the case, I could build a switch like that, I could fulfill this condition. Okay, I found quantum mechanics in this and in that scheme, and there were new schemes, clear violation of Bell's inequality and quantum mechanics. Then there was a third generation of experiment by the end of the 80s. So my experiments were completed in 82. By the end of the 80s, physicists were able to build a new kind of sources of pairs of photons. Mine was better than the one of Clauser. Theirs was much better than mine. And it was better in the following sense. In my source, photons were emitted in all directions, and I had to capture them with lenses. Here, the photons are emitted in well-defined direction, so well-defined that you can fit them into optical fibers. And once you have optical fibers, you can go far away. So Nicolas Gisin in Geneva was able to fit the photon in Geneva here in the optical fibers of the commercial network of Swisscom, you know, the telecom of Switzerland. And so here it's at 4 kilometers, here at 10 kilometers, and it still obtain a violation of Bell's inequality. Meanwhile, Zeilinger in Innsbruck with his grad student Greg Weiss did an experiment where he also had optical fibers. And what he did was changing the orientation of the polarizer while the photons were in flight. But because he had much more time than I had, he could have enough time to run a random number generation to choose the orientation. And then because it was very small in an optical fiber, he could implement a scheme called the Kerr or Pockle cells or Kerr cells or something like that to change the orientation depending on the result of the random number generator. So it was better than mine. It was 16 years later. It's normal that the experiment improve after 16 years. Both found quantum physics. And then there were many other experiments after that. And so the conclusion is that Einstein's local realism is rejected. What is Einstein's local realism is what I have told to you up to now, but I will elaborate a little more, is the fact that the two photons bring along their own property determining the result. Well, it does not work, because if it worked, we would not have found violation of Bell's inequality. So what can we say? What can we conclude from the fact that Einstein's local realism must be rejected? Well, in fact, it's easy. We just have to read Einstein. And at this point, people say, come on, Einstein did not believe in what he was saying. Of course, he did believe, but he was reasoning ad absurdum. He was saying, if I was not right, this is what you would have to swallow. And we have to swallow it. And this is writing of Einstein, okay? He said, if I was not right, you should abandon the independence of the physical reality present in distant volumes, or accept that the measurement on one system here modified instantaneously the real situation of S2. Let me explain a little more. For Einstein, the physical reality present in some volume. When he say volume and when he say distance, he means in space-time, okay? Think space-time, okay? Time and position. And so he say, when I have a volume in space-time, all the properties of the system which is here are determined by parameters which are there and not out of it, or which are in the backwards right cone. Of course, it can depend on the past, but it cannot depend on something which is separated in the relativistic sense. And so he said, if I was not right, you would have to abandon the idea that when you have two systems, the two systems have their own property, and the property of the ensemble is the sum of the property of the first one and the second one. And he invokes another possibility, which is in a sense equivalent, which consists to say, when I do something here, it can change instantaneously. He said telepathically in his book, just to say that he cannot even think of that, but he said, okay, instantaneously, the other one. If indeed what I do here can change instantaneously what happens there, it's not a good idea to consider that they have independent physical reality. Why do I cite the two? First, because Einstein wrote the two sentences, so probably he makes a nuance. But in fact, in terms of applications, these that we call quantum holism will result in the ideas about quantum computing, while the idea of quantum non-locality will result in ideas corresponding to quantum communication. So two lines of applications which are associated more to thinking one way or to thinking the other way. Okay. Before finishing, because now I'm coming close to the end, right, Joseph? Yes? Thank you. He's very useful as a postdoc. I will just give you an example of my claim that accepting non-locality, many physicists are shocked by that, but okay. For me, quantum non-locality is a very useful image. I don't claim that in the real world there is something like non-locality. I just say that in my head, there is non-locality, and there is non-locality that I have in my head and in my images is extremely fruitful because it allows me to have intuitions of things interesting. And then, of course, when I have an intuition like that, I take my equation, I do the calculation, I check that the intuition is okay. But non-locality allows me to have an image which is crazy but fruitful. I show you. What is non-locality? Well, I will pass rapidly here. I will come again tomorrow. But here you have a reasoning which allows you to conclude. I will go in detail tomorrow. It allows you to conclude that until the last moment, you don't know if you are going to get +1 or -1. But at the very moment when you get +1 here, instantaneously, the other photon assumes the right polarization to give +1 at the moment. And you are going to tell me this is crazy. Yes, it is crazy, but it is what my last experiment shows. Because in my last experiment, I wait until the last moment to decide on the orientation of the polarizer. And indeed, the result depends on that last moment polarization. So this image that you draw from that, I will come back on it tomorrow. I pass on it today. This image tells you that you have an image in real space yielding the same result as the calculation in the abstract mathematical space until the measurement on U1, one can get as well +1 or -1, the same on the other side. But immediately after the measurement on U1, if U1 is little first, okay, immediately after, then the polarization of the other one is such that you get the perfect correlation. And of course, why do we call that quantum non-locality? Because it seems to influence instantaneously at a distance what happens. By the way, a remark for my colleagues. Einstein, Polowski, and Rosen were not the first to think of entangled state. Before them, people trying to describe the levels of energy of the helium atom had found that the two electrons had to be entangled. But you know, two electrons around the same nucleus. Okay, it's a strange state. What Einstein realized, I think it is really the genius of Einstein, Polowski, and Rosen, that according to the formalism of quantum physics, this will survive whatever the distance, and not only in the helium atom, okay? And so this entanglement as a distance is absolutely surprising. It's called quantum non-locality. And now I told you quantum non-locality allows me to make good images or fruitful images, and I show you the example of quantum cryptography. You know what is the problem of cryptography? You have two friends, Alice and Bob. They want to communicate secretly, and there is an eavesdropper, an awful spy. And to avoid to be accused to be anti-women, I put a mustache to Eve. And it's obvious that people who have a mustache are bad guys, okay? So this is a bad guy, and he tries to intercept the message. How can they do? There is a classical method invented by Robert Shannon, which is called one-time pad, which says, if Alice and Bob have two identical copies of random series of 1 and of 0, if Alice uses that to code and Bob uses the same to decode, it's absolutely safe. There is no way for the spy to decipher it under one condition. The message should not be longer than the encoding key, because if it is longer, the cryptographist people who are very smart will notice some kind of periodicity, and they will be able to decipher. There are plenty of examples of that, okay? During World War II, the Allies were able to decipher the message from the German Navy by method of that kind. So the problem boils down to distributing these two keys, and for that, these two identical keys, and for that, the pairs of entangled photons allow for distribution of some keys. It's called quantum key distribution with a total security. And then comes a non-locality. So the idea, of course, you have understood, is to have a source of entangled photon. You send one to Alice, one to Bob, and when Alice and Bob have the same direction for the two polarizer, randomly they get +1 or -1. So it's really indeed random, and it is the same. It is how you distribute that. Now, where is non-locality? It is in the fact that if you really accept what I told you, until the last moment, it can as well be +1 as -1. So here, there is nothing to spy. Even if the bad guy spies, here, there is nothing to spy. And let's suppose that he is so smart that he takes a photon, makes a measurement, and sends a photon with the same polarization that the one that he found. Now, you have a real hidden variable. This polarization that he has found is now a true hidden variable, which means that if Alice and Bob try to make a check of Bell's inequality, they are not going to find a violation. So in fact, the full method invented by Arthur Eckert consists of Alice and Bob choose between various orientation. When they finish, they communicate by an open radio to know when they are the same orientation and when the orientation corresponding to the orientation to test the Bell's inequality. And from that, they can check that there is no spy on the line, and they can decide which are the measurements which correspond to the same value and produce a key. Once again, you can make complicated calculation, read the paper by these people. You have one of them here, okay, see. You know, these people who do quantum cryptography are very sophisticated. They do very complicated things. But here, from the beginning, the first time when Arthur Eckert showed me that, immediately I understood why probably it works. It's because there is nothing to spy, period. And this is because of non-locality, okay? So, this is what is written here. So this quantum key distribution works, and it even works from a satellite. Our colleague Jian Weipan in China has a satellite sending pairs of entangled photons, and he can do quantum cryptography at more than 1,000 kilometers. So it has been demonstrated in such a situation. So time to conclude on the second quantum revolution. In fact, second quantum revolution is not only about entanglement. It's also about being able to observe, manipulate, produce, whatever you call it, individual quantum objects. Young people, you may think that it is obvious. When I was a student, nobody had ever done that. Moreover, somebody as smart as Schrödinger has said that we will never be able to manipulate a single object. And you have to understand that in that time, when people thought that the only thing you can do is have a large collection of objects and do measurement of that, they were not annoyed that quantum mechanics makes probabilistic prediction. If you can only observe a large collection of objects, well, the theory which renders an account is probabilistic, it's okay. But starting in 1970, Hans Dehmelt was able to trap a single electron, observe it, make measurement on it. Then people were able to trap ions, to manipulate single atoms with an AFM on the surface of a crystal to produce single photons. Well, these are the single photon of Serge Roche. And there is also circuits, supraconducting circuits, which can be considered elementary quantum objects, two-level system that they can put in one state or another one or superposition. And, one essential ingredient of the second quantum revolution is to be able to manipulate and entangle individual quantum objects. And of course, entanglement is also a major ingredient. So we have a concept, entanglement. We have science. We have observed many phenomena related to entanglement. People working on the many-body problem, I guess that you are going to talk about the many problem, speak of entanglement all the time. Okay, so entanglement is really a new scientific concept, which is very important. And applications, where application, I can show 3 lines of application: quantum communication, including cryptography and teleportation. If you ask me, I will tell you that teleportation is not exactly taking me from here to Paris-Saclay. It's slightly different. There is quantum computing with 2 branches, perfect or imperfect. I can come back to that tomorrow if you want, or now if you ask question. Quantum metrology that works. This apparatus here has been built by my former students. It's a quantum gravimeter, measuring gravitation by falling atoms, having interference between atoms, etc. It works 24 hours a day, 7 days a week, 12, I don't know how many weeks a year, 50 or something, a year on the slopes of the Etna volcano. And the hope is that by measuring so delicately the small variation of gravity, you can anticipate the volcanic eruption. So it's and this is really working. It's quantum metrology. This is NV Center, quantum metrology also. So to conclude, will the new quantum revolution, which is both conceptual and scientific, have a major impact on society? I don't know. What will be the quantum advantage? And now to young people. When you read in papers, in newspaper, people have only in mind that the quantum advantage is that a would-be quantum computer could be able to make calculation more complicated than a classical computer. This is one side of the quantum advantage. But another side of the quantum advantage could be, and there are good reasons to believe that a quantum computer could do the same calculation as a classical one, but with much less energy consumption, much less electricity. That would be another very interesting quantum advantage in the present circumstances of the planet, okay? So nobody can answer with certainty that it will transform the society. I'm pretty sure that there will be niche application, very specialized. Will it change the society? I have absolutely no idea, but many people believe it. Here is just a few examples: France, Europe, Région Île-de-France, but of course you have the same here. All countries have its own program, quantum program. Big companies have their own program. Why? Because they think that there might be important application. And if you are not in the game, it's a big mistake. This is why they bet. It's still a bet, okay, at that time. We don't know if it will transform the society, but it would be stupid not to bet on it, because if you don't bet on it and that other win, you are going to regret it. And of course, there is all these startups. I'm sure I've forgotten several startups here. And it's also exciting for young people who want to develop real devices. With this, thank you very much. And there are questions, Joseph, now?
Yes.
If
Yeah.
you want to ask questions, try to concentrate on question, not too much technical, okay? Technical tomorrow.
There are microphones in the hallway, so please, if you have a question, if you could approach a microphone. Please go ahead.
Yeah. Thanks for an excellent talk. The issue of quantum entanglement, you mentioned how it, seems like you're gaining information instantaneously at a distance. And I know that physicists always say, well, don't worry, there's no conflict with special relativity because you can't use it for signaling. And I'm just wondering, does that mean everything is fine?
I even have transparency on that. Thank you for the question. So this is a transparency. No faster than light signaling. I did not pay him. Signaling means I push on a button here and a light immediately is on here. Or I push on a button and a bomb explodes immediately. This signaling. There is no signaling, and this allows us to touch on one other fundamental properties of quantum physics, you will see. So the idea is the following. Alice, so we have pairs of entangled photon arriving all the time. And you have in mind this idea that when the measurement is done here, the photon going out here is either polarized along the direction of the polarizer or at 90 degrees, and not in other direction. And immediately, the photon of Bob is the same. So it is really polarized either along this direction or along the other one. Can Bob realize that the polarization of his photon, which was maybe A, and suddenly Alice has changed to E prime, can he realize that it has changed to E prime? The answer is no, because from the point of view of Bob, who only looks at that, it still looks like a coin tossing. It's totally random, +1 or -1. So how can Bob know that Alice has changed? By comparing his result to the result of Alice, which means that he needs a wire here to tell him the result that you have here. And then by comparing his own result to this result, he can tell that Alice turned that. But, this is a classical channel, cannot go faster than light. So he has to wait. So there are several consequences on that. First, realizing that many quantum operations at a distance, such as quantum teleportation, tomorrow I will tell you a little more about quantum teleportation, they have two channels. A quantum channel which looks instantaneously, and a classical channel which is not faster than light, and you need to have the two channels joining their results to complete the operation. And what is a fundamental quantum property which is at use here? It's the fundamental randomness of a measurement. If Alice could say, okay, for the next 100 photons, I decide that they will all go to the +1 channel, then Bob could know. But the fact that Alice cannot control, that's either +1 or -1, she cannot do anything against that. This is what guarantees that you cannot communicate faster than light. And there is a second thing, which is not written on this transparency, is a no-cloning theorem. Let's suppose that here you could clone the photon with its quantum state. So you have a photon polarized like that. Now you make 2, then you make 4, you make 8, etc. And now you use 8 different polarizers with different orientation. Just by looking at the statistics, you could know what was the state of the photon arriving. But there is a no-cloning theorem which tells you that in quantum physics, you cannot clone a system with the totality of the quantum state. You can reproduce a fraction of it, or you have quantum teleportation, and this again tomorrow, come tomorrow. Well, I ask for not technical, and at the end I do something which is technical.
In your talk, you suggested that Einstein would have accepted these results if we read what Einstein said correctly. Now,
Speak closer to the microphone, please.
in your talk, you suggested that Einstein would have accepted these results if we read closely what Einstein had to say. Now, we don't necessarily have to presuppose. Rosen was still alive at the time these experiments were conducted.
You speak too fast for me, excuse me. I am an old man and a Frenchman, both. So
Rosen was still alive when these experiments
Yes.
were performed.
yes,
Do you know what Rosen had to say about,
Well,
did he contact you? Did you ever
I
meet him?
met
What-
Rosen.
And what did he have to say about the?
Well, he has to say that's okay. I have to admit that it is like that. You know, I am writing a book, and the title is in French, Si Einstein avait su. And I will make hypotheses about what could have been the reaction of Einstein. And maybe I don't want to spoil the book, so.
Yeah, but did
So
Rosen-
when it is published, and when it is translated in English, it will take at least another year. You can buy it. But it's a very good question. But there is no doubt that Einstein was perfectly rational. Okay, for me, what strikes me in the debate between Bohr and Einstein, at the end of the day, Bohr is right.
Okay, but that's speculation,
But Einstein is clear, and I'm pretty sure that at the end, Einstein would have made a conclusion. Allow me to say something which is true, but it's also kind of a joke about Bohr. You know, Bohr was all the time speaking of complementarity. And one day he said that clarity and truth are complementary. And Bohr did all efforts to be as true as possible. This is not a joke. Eh? He really wrote that. Not that he made effort to be true, but that truth and clarity are complementary. Einstein was clear. And so, but Rosen, I met him. He was an old man. I met him in Technion in Israel. And he had not much to say rather than to say, okay, Bohr was right. And that's it.
Thank you so much for your talk. You mentioned that this mathematical formalism led to describing observed phenomena, predicting new phenomena, and inventing new devices. I'm curious, with the advent of quantum computers and what's been happening today, if you also see a revolution in information coming along,
Yes,
since there's a
absolutely.
lot of problems that need to be turned
Yeah.
into NP-hard problems that doesn't
Yes,
exist.
absolutely. This stems from something I'm sure we are going to hear from the next speaker. The many-body problem, that is to say, entangling several objects, opens an immense number of possibilities, and quantum computing is one of these possibilities. So there is no doubt that quantum computing is very much related to entanglement of many systems, okay? And the extraordinary thing, well, I anticipate to tomorrow. The extraordinary thing is that if you entangle many qubits, but many is not 1 million, only 100 qubits, the amount of information that you can put into that is much larger than the total amount of information that you can store in all the computers that we have on the world. I think that it is probably something like 70. With 70 qubits, you could store the whole information that we have everywhere. So you see, this is why it's fascinating, because the size of the Hilbert space in which you work explodes exponentially. And again, if we have 100 qubits, it's well beyond our imagination. And this is why people work so hard on building a quantum computer. Is strictly related to the potentiality of entanglement. I hope I do not spoil your talk.
Right, seeing none. Thank you
Merci.
very much.